Okay, so welcome everybody. It is a pleasure for us to present you Daniel Sudarsky, from professor from Universidad Nacional Autónoma de Mexico and from John Bell Institute. He's a recognized expert in semiclassical gravity, and today we'll talk about semiclassical gravity and its applications to cosmology. So please, Daniel, when you are ready, you can start.
Okay, thank you. It's very nice to be here in this community and share with you the ideas that we have been working for some time now. I will not be specifying each particular work was done with which collaborators, but here is a list of the most recent collaborators, including a couple of people present in the talk, and there are several other people that have worked in these lines for several years that I will not be mentioning everyone. Okay, so the basic issues that we have been interested in dealing with is considering how to treat gravitation together with quantum mechanics, but recognizing that quantum mechanics, as we understand it, is not really a satisfactory in a satisfactory form for a fundamental theory. As you know, the theory is plagued with the issues normally referred to as the measurement problem. I like to call it the M problem to indicate that I regard them as very, very serious. And among them, there is a lack of a clear ontology. This word, is not very popular among physicists, but basically the issue is that the theory is not very clear in what, according to itself, the theory itself actually is out there in the world. And as John Bell emphasized, this is something that we would need a satisfactory physical theory to do. Normally, when we talk about those issues, we regard these things that exist out there in the world as localized in four-dimensional space-time. These better be local variables rather than simply observables, in the sense that we should be able to talk about them without having to talk about a particular sapient being that is conducting observations on the issues, particularly when we want to apply it to realms like cosmology. And as I said, these questions should be framed in space-time. Of course, in most practical situations, everybody knows that we can rely often on intuition to identify what are the relevant physical observers and even identify which mathematical objects we use to represent them, usually self-adjoint operators. But in generic situations, this is problematic. And I would like to emphasize this point by giving a very simple example. The issues at hand were considered by Mott early in the last century, during the first stages of the development of quantum mechanics, when he was studying or questioning how we account for a track of an alpha particle that results from a decay of an excited or of a radioactive nuclei. Here we have what we call a mini-Mott version, which is a much easier to treat example, but that contains all the relevant issues. So imagine that we want to describe the detection of one particle, but instead of having one detector, we place two detectors, one at position X and one at position X0. To simplify the description, we use simply two-level detectors that are excited or unexcited. For each one of them, we can write their, intrinsic Hamiltonian in the fashion written in equation 1, where the first I sub p indicates the identity regarding the particle degrees of freedom. The particle is, of course, described by its free Hamiltonian, and of course we need to to include some interaction between the particle, and here is the Hamiltonian interaction with the particle number one, with the particle detector number one, which basically, if the particle is located at the position where the detector is located, then the interaction would excite the system if excite the detector if the detector was unexcited, and of course do the opposite. That's what the Hamiltonian does. And we would have a similar expression for detector 2. So the setting is simple enough that we can write the expressions for the initial state and the solution basically in an explicit form, if we consider the initial state to be represented by a particle whose wave function is, let's say, a symmetric Gaussian around the origin, then we can write the initial state as written in the first equation, and after some time write the resulting state coming from this evolution in the way depicted in the second line, where we would have components in which the first detector was excited, another component in which the second detector was excited, a third component in which no detector is excited, and a fourth component, a little bit puzzling, in which the two detectors are excited. The last two terms are normally identified with, well, no detection. No detector is, perfect detector, so the no detection possibility should be present, and a double detection that would be described as indicating some scheme, some setting in which we would say the particle is interacts with the first detector, and then it bounces back and interacts with the second detector, or something like that. Anyway, here we would be tempted to read the first two terms as indicating that the particle was detected at the first detector or the second detector. In each of these two cases, we would say the symmetry of the system, which was symmetry x goes to minus x, detector 1 goes to detector 2, is broken. But of course, here we would be using our intuition. And to see that this intuition is problematic, we can easily write a different basis for describing the setting, in which, again, I leave the double detection and the undetection states of the detectors unchanged, and then I have a symmetric characterization of the detectors, of the excited detectors, the symmetric and antisymmetric states. And in that case, the wave function after time t could be easily written in this other framework. And the question we want to consider, which of course here has a very simple answer, but in general it does not, is whether we should rely on the interpretation based on the first scheme or the second scheme. So this illustrates one aspect of the measurement problem. And here should be clear that all items, all aspects of the problem that are describable in terms of standard quantum mechanics have been provided for and have been taken into account in this description. And nevertheless, without the reliance on some intuitive notions, we cannot answer the question of which one is the way, which one is the correct interpretation of the problem. In the case of gravity, or the interference of gravity and quantum, one may imagine that a setting like I have just described would be superseded by something deeper, some quantum gravity theory, in which perhaps space-time itself is regarded as emergent from some more fundamental structure. But the truth is that at this time, we simply do not have any proposal that can solidly deal with these issues. To emphasize this point, let's consider, a thought situation in which we have, let's say, a moon in a superposition of two different locations. Here we have a nice picture taken of that setting. But of course, we would not be able to describe something like that in any existing setting that we have. And the issue is not just technical, it's fundamentally conceptual issue, we do not know how to describe the superposition of two spacetimes. This issue has, in fact, been considered in the analysis within the semi-classical context of an experiment, a famous, somehow famous experiment by Page and Gleicher, in which a system in a mass is placed in a superposition of being in two places, the right and the left, and made to interact gravitational with a probe, a Cavendish-like torsion balance. And after doing this experiment, I don't want to get into the details of the experiment because there are some, criticizable aspects of the experiment, but nevertheless, I think the conclusions are straightforward. Basically, they conclude that if there are no collapses of the quantum state, then the theory is in conflict with the experiment. Basically, they see the Cavendish torsion or the torsion balance moving towards one direction, while the symmetry of the system without the collapse would imply that the torsion balance could not have moved in any direction. And on the other hand, if there are collapses of the quantum state, the theory is simply inconsistent, basically because such a collapse is normally associated with the violation of the conservation equation for the expectation value of the energy momentum tensor, while the left-hand side of Einstein's equations would, of course, have vanishing divergence. So this illustrates a very serious problem if one wants to consider semi-classical gravity. In fact, this description was done considering a collapse of the quantum state as the possible outcome. In this paper I have cited there, we have argued that all reasonable paths to deal with the measurement problem led to exactly the same problem, namely violations of the object that we would put in the left-hand side of Einstein, on the right-hand side of Einstein's equations, namely something representing the quantum energy momentum tensor of matter fields. Actually, those three reasonable paths, let me name them for you if you are not familiar with this, are provided by Tim Modlin's trilemma, which basically says that the three following statements cannot be simultaneously be taken as true. And the three statements are, first, the characterization of the system by the wave function is complete. Its negation leads to things like hidden variable theories. The second is the evolution of the wave function is always follows the Schrödinger equation. Its negation leads, for instance, to spontaneous collapse theories. And the third one is the result of experiments, of concrete experiments, led to definite results. And its negation leads to things, approaches like many worlds, many minds, consistent histories, approaches, etc. Furthermore, I should say that in canonical approaches to the issue, like loop quantum gravity, we don't even know how to recover space-time. That's the status of that program. In other settings like string theory, one relies in practice on splitting the metric and anything else into a classical background and small perturbations that are themselves subject to a quantum field theoretical treatment. However, here I want to emphasize that making this separation and using quantum field theoretical treatment of the perturbations is in principle rather problematic. This is emphasized, for instance, by Wald in his book, 1984 book. As an example, let's consider separating the metric into a background metric that, let's say, we will treat it classically, and a perturbation of the metric. And if one tries to implement the microcausality requirement for the quantum field theory of the perturbed metric, one would say, well, one would impose the commutation relationships that I've represented in equation 7, but those are meant to hold if X and Y are space-like. But the notion of space-like, of course, would be implemented using the notion provided, the notion of causal structure provided by the background metric, rather than that associated with the metric itself. So effectively, that would avoid the quantization of the causal structure while retaining the quantization of the metric structure, making it a coupling that is very unsatisfactory from the conceptual point of view and clearly violating of the idea of general relativity. So let me say now a word about methodology. How do we approach this setting? Well, our idea of how to approach this issue is to take what we like to call a top-bottom approach. And that is to be contrasted with the standard approaches, the bottom-up approaches, which basically postulate some fundamental theory. One assumes one is given somehow the fundamental theory of nature, string theory, quantum gravity, etc. And one then attempts to connect with the regimes of interest in the world out there. The top-bottom approaches is perhaps less ambitious, and I think, on the other hand, more conservative, is the idea of pushing existing well-tested and developed theories to address open issues that seem to lie beyond them, trying to look for modifications that could serve as clues about the nature of the more fundamental theory. So this second approach is in a sense more humble, taking the view that we still have many things to learn and perhaps find some guiding principles to construct the fundamental theory. So again, the idea is to push GR together with quantum field theory in curved spacetime, while considering at the same time the fundamental issues that I described at the beginning. One aspect of that type of analysis is that needs to be taken into account is to consider carefully some notions that are employed sometimes in a conflicting way, or in a way that conflicts with the basic setting of the program. And here I'm talking about how we treat or how we think about quantum fluctuations. The very terminology is one that promotes the confusion of quantum uncertainties with stochastic fluctuations, which in turn can refer to either changes in some system occurring in time or variations in localized aspects of standing systems. For instance, the surface of a lake where the water changes at every point in the space-time description of the system, or among individuals within an actual ensemble. So we should avoid making this confusion, which is rather prevalent in applications to cosmology in particular. Where do we find these issues appearing? Well, they appear in the treatment of the emergence of the seeds of cosmic structure during inflation, similarly in the generation of primordial gravity waves during inflation, and finally they occur as the underlying reason for a problem that seems to afflict most inflationary models, which is called the problem of eternal inflation. I, of course, remind you that quantum uncertainties may be identified as measures of a stochastic kind, but this stochasticity refers to the outcomes of a measurement performed of the system. It means an interaction of some external device with the system that modifies the state of the system. And without absent a measurement and this interaction with an external device, then we have a very, very clear and serious version of the M problem. In the cosmological context, of course, is one that no observer or measuring device can be identified. We don't want to call upon a god or something like that. And I should emphasize that simply overlooking these conceptual issues and adopting, let's say, a very practical posture when one thinks of the system just jumping around within the corresponding uncertainty range is untenable. It's untenable both at the conceptual level, but also because it leads to conflict with actual experiments. An example of one such experiment is the current bounds that are established on the electric dipole moment of the neutron, where the uncertainties can be readily estimated to be of that magnitude, 10 to the minus 14, 10 to the minus 15 electron charge times centimeters. And on the other hand, the bounds that have been achieved on this quantity indicate that the electric dipole moment is smaller than a quantity that is at least 10 orders of magnitude smaller than the quantum uncertainties. Thinking of the quantum uncertainties as indicating that the system is jumping around the values within that range simply leads to the conclusion that no such bound would be achievable with any experiment. Okay, this is a paper we published recently that I think helps drive the point very, very clearly. Well, so let me now get to cosmic inflation. As you all know, contemporary cosmology takes inflation as one of its central aspects. It represents a very early stage of extremely rapid acceleration in the expansion of the universe, and that's supposed to last around 60 e-folds or so. During this period, the universe is meant to become very, very homogeneous and isotropic if it didn't start that way. And actually, most defects that could have been created in early processes like phase transitions would be exponentially diluted, and other naturalness problems like the flatness or horizon problems are equally readily solved. The simplest version of the theory is described by the action represented in expression 8, which is just Einstein-Hilbert action coupled to a scalar field with a single scalar field with a potential, and the potential would be slowly varying in space-time because it's a function of the field that is meant to be also slowly varying in cosmic time, and this would act basically as a cosmological constant that is producing this extreme acceleration. However, besides solving these problems, the biggest success claim by inflation is its account of the emergence of the seeds of cosmic structure as a result of quantum fluctuations. And this comes naturally with the correct spectrum. However, at the conceptual level, this is simply not satisfactory because of the things that I already mentioned, because one would be interpreting quantum fluctuations as if they were stochastic fluctuations, and they are not. So the starting point of the analysis of this generation of structure and of other issues as well is to describe the space-time choosing a gauge for simplicity as a background Friedman-Robertson space-time characterized simply by the scale factor A of eta. Eta is the conformal time, and where I have put already in the expression for the line element the quantities that represent small perturbations that contain the possible spatial dependence on of the system or of the space-time metric. This would be what's called the Newtonian potential, the quantity psi represented there, and the tensor modes represented by the Hij object present there. And of course, the field also is the scalar field, the inflaton field is also represented by its background, which is a function only of conformal time and small perturbation that is also possibly spatially dependent. The background is assumed to be dominated by by the effects of this inflaton potential, what's called this slow roll regime, and therefore phi0 changes slowly, and the scale factor changes almost as expressed there as 1 over eta in conformal time. And the setting is one in which we, let's set the scale factor A equal 1 for today, and the inflation taking place in these particular values of the coordinates. Okay. The key point is that the perturbations are now treated quantum mechanically. That is, using quantum field theory and curved spacetime on the given background, and treating these objects, this particular combination of scalar field perturbations and metric perturbation appearing in the so-called Mukhanov-Sasaki variable, and also the perturbations of the characterizing the tensor modes. And these fields are supposed to be characterized or represented by the, or their state is supposed to be represented by the Bunch-Davies or adiabatic vacuum state, basically because of the idea that inflation will dilute all pre-existing features and drive the space-time dependent fields towards the vacuum state. The first thing we should note is that in doing so, one is, in treating these objects quantum mechanically, one is doing precisely the type of conceptually problematic scheme we discussed before, that is, quantizing the perturbation of the space-time metric, but not the space-time metric itself. So that doesn't seem to be completely satisfactory. But even more seriously is the problem of the interpretation that is given to these results. Again, these fields in those particular states are characterized by quantum fluctuations or quantum uncertainties besides their expectation value. And here we find the kind of confusion in the use of this notion that we discussed before. As I said, these quantum indeterminacies are unjustifiably identified as primordial inhomogeneities, which eventually evolved and created all the structure that we see in our universe, galaxies, stars, planets, and so forth, and that leave their traces in the cosmic microwave background. However, as we see, as we noted, in the inflationary picture, the universe was homogeneous, completely homogeneous and isotropic, both in the parts described classically, the background, and the part describing quantum terms, because the Bunch-Davies or adiabatic vacuum are perfectly homogeneous and isotropic. So reading into them inhomogeneities and anisotropies is simply unjustified. Of course, the present situation of the universe involves galaxies and stars and so forth that break the homogeneity and isotropy of the initial setting. And this is simply something we cannot account for if the dynamics of the closed system, we don't believe anything exists outside space-time, break those symmetries. So here we have an instance of the measurement problem becoming, very clear and very, very problematic, more than usual. So what do we do in this regarding this problem? Well, the idea is to address the measurement problem and try to implement or treat the situations at hand with a modification that addresses that problem. The approach we have taken is to take the path of collapse theories, which are basically schemes that unify the unitary and reduction evolutionary processes appearing in quantum mechanics. These theories, of course, have been subject of lots of work. the first version of this, the first workable version of this theory is called the GRW, or Girardi-Rimini-Weber theory. There is another version, continuous spontaneous localization, by Philip Pearl. There are now some relativistic versions, and also Lajos Diosi and Roger Penrose have considered these theories and tried tying them with their intrinsic dynamics in a fundamental way to gravity. So let me write for you an example of these theories, in particular the continuous spontaneous localization, which is basically a modification of the basic dynamics produced by Schrödinger equation, and represented by the solution of the equation, which is somehow simpler to write than the equation itself, that we see represented in equation 9. Here we start with a system in a state at time equals 0, and we write the state after the evolution at time t, and we see that we have a part of the evolution that is simply the Hamiltonian dynamics, and then there is a correction term that is characterized by three items, three objects. One is a stochastic function of time, and that W is also being labels the evolution to indicate this is the evolution of the state if the stochastic noise happened to have that particular realization. The other two items represent the strength of the deviation from standard unitary evolution, represented by the parameter lambda, and A is the so-called collapse operator, which tells us toward which type of states does the collapse try to drive our initial state. Yes, there was a question somewhere? No? Sorry. Okay. Okay, since the evolution is now not longer a unitary evolution, we need new rules to talk about probabilities. For that, we don't simply compute amplitudes. Probabilities are not longer computed by simply computing amplitudes. They are, however, related. Equation 10 tells us what is the probability or the probability density for the realization of a particular stochastic version of the noise W of t for a function W of t that is in each time interval, in each time ti in the interval is located in the little window dW of ti. Okay, I don't want to get too much into the details of this formulation. Just let me mention that in the setting of non-relativistic particle multi-particle quantum mechanics, the collapse operator is taken to be the smear position operator, which of course is not something that we will use here. The parameter is supposed to be small enough to avoid conflict with test of quantum mechanics, and on the other hand, big enough to ensure a rapid localization of macroscopic objects. The parameter range that is being suggested is something like 10 to the minus 17 seconds, indicating that for one particle, there is one collapse more or less in the age of the universe, but for 10 to the 32 particles, like in any macroscopic body, we would have collapse in very small fractions of a second. The interesting thing is that these theories now can account for the breakdown of symmetries, and therefore we consider incorporating those into the inflationary cosmology setting. They, of course, involve modified evolution of the quantum state, and since it's a modified evolution in spacetime, we need spacetime in order to even write them, and therefore we are prompted to treat spacetime as classical. So we are prompted to treat spacetime as classical because we need to have good notions of spacetime, but also because at this point, as I mentioned, we don't know how to treat spacetime any other way. The scalar field is nevertheless going to be treated using quantum field theory in curved spacetime, and this basically takes us to the semi-classical gravity setting. The natural ontology for a theory like this in the case of CSL or GRW, is normally taken to be something like the mass density ontology, where this combination of mass with the square of the wave function is interpreted as the actual mass density present in space-time. In the case of when we want to adapt this to a GR kind of setting, we replace it with the expectation value of the energy momentum tensor. So that would be playing the central role of the ontology in our theory. Again, our view is that semiclassical gravity, together with any resolution of the measurement problem, is not to be considered as a fundamental characterization of the interface of geometry and quantum aspect of nature. Is simply an approximate characterization, but the best we can do. And therefore, we view, in our case, semiclassical gravity together with an adapted version of spontaneous collapse theory as an approximated description that we should consider in analogy with hydrodynamics, in the sense that the theory is described by equations, but these equations are not sacrosanct in the sense that they are not supposed to hold at all times, just in a broad enough set of circumstances. But of course, being not fundamental, they would be subject to breakdown. The theory would break down. So like a wave in the ocean that is described by Navier-Stokes equations, we have a very nice description before the wave breaks in the beach. When the wave is actually breaking down, approaching the beach, degrees of freedom that we have that are not described in Navier-Stokes setting are excited, and we need a more fundamental description that for the case of hydrodynamics we have, for the case of our theoretical setting we don't. But nevertheless, we know that even if the description breaks down during that particular moment, after the wave breaks down and the foam goes away, we are still back. We are going to be back in a setting where we can use the Navier-Stokes equations and describe, for instance, how the wave recedes from the beach after breaking down. So we take the collapse. We take the collapse theory or semiclassical gravity with collapse theories in that spirit, thinking that during the collapse events, the equations will not hold, but they would hold before and after the collapse. And we will take the collapse to take place in very, very small time intervals that we will not try to describe. So let's start making things a little bit more precise and concrete. So we will then be taking a generic framework to characterize the situations in this setting using semiclassical gravity and quantum field theory. And for this, we will use what we call the semiclassical self-consistent, the notion of a semiclassical self-consistent configuration, which is basically the setting in which the fundamental equations of our theory is supposed to hold. Again, this setting is not supposed to represent every single moment in the evolution of our system. So what is the setting? Well, the setting is a space-time metric with a quantum field theory constructed all over that background metric. So we would have, field operators acting on a Hilbert space and a particular vector in that Hilbert space, which is required to satisfy the equation that we have below. So this equation below is basically the Einstein equations sourced by the renormalized energy momentum tensor computed in that particular state. Let me not say more about this in the moment. But of course, this setting is one that we should recognize as being self-referential in a sense, because the space-time is, in some sense, connected to the state through these last equations, but the state, of course, belongs to a Hilbert space that is the result of the construction of the field theory in the background of that space-time. So it's a setting that involves self-reference in complete analogy to the Schrödinger-Newton system that you probably are familiar with. So this would be in our view, the GR version of the Schrödinger Newton system. Of course, then, if we want to incorporate the spontaneous collapse, we would have to view it as not simply a change in this quantum state, but a change in the quantum state that is accompanied by a jump in the space-time metric. So the jumps, or the quantum jumps that will be described originally by our collapse theory, are now promoted to jumps in the whole setting, including the quantum space-time. So if we are going to have such a scheme, we need to not only describe exactly how the collapse occurs, but also describe how to join the two semiclassical self-consistent configurations on the collapse hypersurface. And for that, we need some matching conditions for both the space-time and the states. And this issue is one that involves very delicate problems, requiring both the complications in the normalization of the energy momentum tensor, well-posedness of the initial value formulation of semiclassical gravity, etc. And furthermore, we need an extension of any collapse theory from the non-relativistic quantum mechanical setting to the setting of relativistic quantum field theory, which is highly non-trivial. Applying the problem to inflation would involve considering the zero mode of the field and treating it quantum mechanically. As we said, all matter fields will be treated quantum mechanically in this kind of settings, and to be represented in this case by a highly excited but sharply peaked state, probably a coherent state, while the space-time dependent parts are initially thought to be represented by the Bunch-Davies or adiabatic vacuum state. The semiclassical equations will be taken to hold in that situation, and one would then need to describe this initial situation previous to the emergence of structure in terms of the dynamics of the expectation value of the zero mode of the quantum field. And later on, we will talk about how the actual inhomogeneities and isotropies arise. We have studied this issue in the case of an individual collapse of a single mode of the inflaton field using the formalism and some natural gluing recipe. We have found that it is constructible. More recently, with Benito Juarez, Tonatiu Miramontes, and Bernard Kay, we have studied the initial value formulation and generic collapse recipes for rather general situations. This work was very complex, very mathematically complicated analysis. Not all the questions were 100% answered in a complete way, but very important progress was made there. Okay, so I'm not going to tell you too much about that. The important thing is that the setting, treating this within this setting, as we showed with the Alberto Diaz, leads to results that can be reproduced by a much simpler treatment. That is what I'm going to describe today. It's a practical procedure that, as I said, gives basically the same results. So now, concentrating back on the space-time dependent parts, the quantum field and its momentum conjugated are taken to be in the Bunch-Davies vacuum state, and their corresponding wave functions for those particular modes are wave functions centered around the origin with uncertainties delta of delta phi sub k and delta pi sub k, the field in the k mode of the field and the momentum conjugate for the k mode. The space-time metric was that is treated classically has the space-time dependent parts vanishing as both the Newtonian and the Newtonian potential and the tensor mode part. However, once and of course, nothing is going to take us from there unless there is some change in the state. What changes the state? Well, the quantum collapse will modify the state, and by modifying the state, will in general modify the expectation values of these quantities. And assuming that the collapse occurs mode by mode and is described by an adapted version of collapse theories, one could recuperate or recover the basic results of the inflationary treatment. So in this view, our universe would correspond to one specific realization for the stochastic wave functions, one for each one of the values of k, of the wave number of the mode. And if we first center on the scalar perturbations and the Fourier decomposition, Einstein's semiclassical equations will give us equation number 12. So there we see that if the expectation value of the momentum conjugate of the field in the mode k is 0, as it is in the Bunch-Davies vacuum, we would have vanishing Newtonian potential and no seeds of structure whatsoever. Of course, if the state of the field undergoes a quantum collapse, equation 12 would change, will now acquire a non-zero vacuum expectation value for the momentum conjugate, and as a result of that, the semiclassical setting and the SSC scheme will indicate that the Newtonian potential acquires a component a k component for its Fourier transform. With that, one can recover or rewrite the full Newtonian potential as a function of x and time. Okay, let me not go into the details of the calculation, but I can tell you that using the continuous spontaneous localization version of the theories and taking the collapse operators to be either the momentum conjugate operator or the field operator with a rate of collapse given by this expression. So it's a constant times k to the appropriate, the wave number up to the appropriate factor fixed by dimensional considerations, or alternatively using collapse operators that are related to the quantum field or the momentum conjugated by these relatively simple expressions. One obtains a result that is compatible with the observations, namely scale invariant spectrum. Why is this the right thing? Why is this the correct thing to do? I don't know. I can tell you that this is correct dimensionally, but I don't know why this turns out to be these relatively simple expressions are the things that are there. We're still trying to understand this. The important thing, however, is that the resulting prediction for the spectrum is expression 13, which is very, very similar to the standard expressions obtained from inflationary calculations using the wrong interpretation, the incorrect and problematic conceptual problem. If we, moreover, take gut scale values for the inflationary potential and standard values for the slow roll, one finds agreement with observations if this parameter lambda tilde is ordered 10 to the minus 19 seconds, inverse seconds or hertz, which is not very different from the GRW suggestion, which is kind of encouraging. Not definite, because of course the collapse operator here is very different from the one that is being used in particle physics setting. There have been other studies along these lines that have made different assumptions and obtained very different results. But let me, after, if you want, adjusting things so that we reproduce the appropriate spectrum for scalar perturbations, go on now and consider the tensor perturbations. So for the tensor perturbations, semiclassical Einstein equations basically reduced to equation number 14, again going to the Fourier decomposition that takes the form of equation 15, where the source term is now expression 16. But we note that now we have a quantity that is quadratic in the collapsing fields rather than linear, as in the previous case. And that leads to a very different type of result regarding the values that one expects for the tensor modes. Okay, well, the first problem we need to deal with is that this expression is formally divergent. However, there are very good reasons to think that there is something that dampens these oscillations at very high values of k. For instance, silk damping. Let me not get into the details of that. But in this case, the prediction for the power spectrum of the tensor perturbations turns out to have expression number 17, which is very different from the standard expression for that quantity. Among the differences is that the value of the inflationary potential appears squared rather than linearly in expression 17. That is a result of the fact that the perturbation the tensor perturbations are sourced by terms that are quadratic in the collapsing field. That's also the reason that we have lambda square appearing in equation 17 rather than lambda. While the scalar perturbations take, I just rewrite it again, take the form of expression 18. So you can see that expression 17 for normal values of, for sub-Planckian values of the potential is much smaller than expression 19. So this is a very different relationship between the prediction for the relationship between the predictions for the scalar and tensor spectrum compared to the standard calculations. In the standard calculations, the two quantities are very close, related by small details, and so they are expected to occur more or less at the same order, while here 17 is evidently smaller than 18. So that means that in this setting, the predictions for the tensor modes are substantially reduced with respect to the standard predictions. This is reported in these papers that I've mentioned there. And the graph comparing the two predictions for the tensor modes is illustrated here. We see the red line is the standard prediction from standard inflationary treatments for this particular potential, and the lines blue and green are the predictions, one using the CSL theory and one using something else, which is basically GRW implemented in a particular way, are substantially reduced. So this, in a sense, is a prediction that is more in accordance to current experimental situation than the standard prediction. In the standard setting, the fact that we have not observed primordial gravity waves represents a serious problem for inflation and serves to discard the most attractive inflationary models. What represents normally is taken to represent a very serious problem. In this setting, the prediction is completely different. Sorry, there was some. Okay, and finally, let me go to the eternal inflation issue. So an issue that is considered one of the most serious problems afflicting the inflationary paradigm is the propensity of simple models to lead to a condition that inflation is essentially unlikely to ever end. So how does this argument work? The idea is that inflation is driven by the zero mode of the inflaton, which while setting in the slow roll condition, fixes a value of an effective cosmological constant represented by the value of the potential, and it is the expectation values, or this quantity is subjected to a characteristic displacement in a given interval of time in a Hubble scale time, in which the field slowly decreases towards its minimum, changing the effective cosmological constant. However, it is argued that the field is also subjected to quantum fluctuations, and in that case, since these are expected to be random, one needs to determine whether these quantum fluctuations dominate over the classical displacement or not. In the later cases, in the case in which the quantum displacement is larger or comparable to the classical description, the classical displacement, then there would be, the argument is there would be situations in which there would be increases in the inflaton, in the value of the inflaton, and therefore increases in the inflaton potential, which represent increases in the effective cosmological constant, and the opposite in other parts. The problem is that the former regions in which the cosmological constant increased will grow faster, and at later times they will represent a larger portion of the universe, and in time the regions where the fluctuations were mostly upwards, in the direction of upward values of increasing value of the inflaton potential, would represent the overwhelming portions of the universe. So we are very likely to find ourselves in one such region, and therefore the expectation is that inflation would never end. Okay, so this is the essence of the argument, comparing quantum to quantum displacement and classical displacement. The quantum displacements, again, are extracted from the estimates of the quantum uncertainties. Well, as should be clear now, this raises serious concerns. Once again, the argument conflates quantum uncertainties with stochastic fluctuations. Quantum fluctuations by themselves do not indicate that something randomly is changing in space or time, as we emphasized at the beginning of the talk. Moreover, the inflaton is driven by the inflationary zero mode, by the zero mode of the inflaton, by the homogeneous anisotropic mode of the inflaton, and therefore nothing pertaining to it could be taken as indicated that something happens in some regions and something else happens in others. So as it stands, there seems to be no solid argument for eternal inflation. However, we had to introduce a stochastic aspect into the dynamics to be able to account for the emergence of structure. We needed to introduce this collapse dynamics that contains a stochastic feature that actually changes the expectation values. Once we introduce this, then we are back into the situation where stochastic modifications in the dynamics can produce actual fluctuations in the value or the expectation values of the field, and therefore we again face the danger of being in a situation where eternal inflation would be a problem. So we need to face the issue again, anew, but from a very different perspective. What we need to compare now is the classical displacement in a characteristic time with the stochastic mean displacement during the same time, that is the stochastic displacement due to the collapse. So we will take the implementation where the field is taken to be the collapse operator with the parameter lambda equal lambda times k, as we indicated, is what's needed for an appropriate prediction, an appropriate power spectrum. And in this setting here, the first thing one would think is that, the zero mode, having k equals 0, is simply not collapsing. So the problem would would seem to disappear. However, we have to confront the fact that there are modes that have such a long wavelength that they could be or should be regarded as effectively acting as the zero mode. Those are the modes whose wavelength is larger than the, let's say, causal horizon or particle horizon. So I'm going to describe those modes as having k star. So the modes that have k smaller than k star, this critical value of representing the causal horizon, are the danger modes. And therefore, we have to compare the stochastic fluctuations due to the collapse dynamics associated with those modes. That means we need to compute this collective displacement represented by this integral and compare it with the classical displacement for all times during the inflationary period. We have analyzed this originally without making any modification, and then we realized that we needed to introduce a modification. So we introduced a slight modification in the collapse dynamics to ensure that we still recover the standard inflationary power spectrum, but modify things only in extremely long wavelengths, so that they will not be visible in empirical studies, which are sensitive to values of k in the regime that I showed. And well, this study was carried on in collaboration with my student, Rosa Laura Lechuga, and published in this paper there. And let me just show you what is the graph of the region in which eternal inflation problem is avoided. So we have a region in parameter space marked by yellow, which is a region in which the eternal inflation problem is solved, is avoided. In the other region, the eternal problem would still be there. So a satisfactory picture would emerge if we take values in that region. Moreover, now we are carrying a detailed analysis of that model with that modified spectrum. This has not come out yet. This is work in progress, but the preliminary results indicate that this modified collapse dynamics would lead to an improved matching of the power spectrum for the low part of the low values of L, meaning the long wavelength part of the spectrum, as compared to the standard one. Okay, so to end the talk, let me just say that this approach seems very promising in addressing other outstanding problems that we face in theoretical physics. Among them, the black hole information paradox, represented in the papers that I'm citing there, as well as the problem of time in canonical approaches to quantum gravity, briefly described in the paper that I described there. Of course, there is still a lot of work to be done. We are probably just at the beginning of the exploration of these issues, but I hope that you will share with me the excitement about the perspective that this approach seems to offer. Thank you very much.